Welcome back to the Deep Dive. Today we are heading way back in time, deep into ancient Australia. We're going to be talking about a creature that really just forces you to rethink the word predator.
We really are. We're talking about the largest lizard to ever walk the planet, Varanus priscus.
Better known as Megalania.
Exactly. And you might think you know about Australia's dangerous animals, the crocs, the snakes. But if you go back 50,000 years to the Pleistocene, Megalania was on a whole new level, a completely different scale of deadly.
The Lost Lizard King. I love that name for it.
It really earned it.
Okay, so that's our mission for this deep dive. We need to figure out the puzzle of this thing. How big was it, really, compared to what's alive today? What made it such a terrifyingly effective hunter?
And the big one, the central mystery. Why did it vanish? And more specifically, why right around the time people showed up in Australia?
It's this incredible intersection of biology and, well, human history.
Right. But before we get to the extinction, we have to really build a picture of what this animal was, the sheer biological terror of it.
Let's start there then, with the size. Because honestly, the numbers are they're mind-boggling. Our best comparison today is its closest living relative, right? The Komodo dragon.
Varanus komodoensis, the largest lizard alive today. And it's a beast in its own right. You're looking at, maybe 3 meters long, 70 kilograms, a formidable animal.
A truly formidable animal, but Megalania just dwarfs it.
It's not even in the same league. We're talking estimates of up to 7 meters long, and the weight, potentially up to 2,000 kilograms.
2,000 kilograms, that's 2 tons.
2 full tons of lizard. Yeah.
But to put that into perspective for you, 7 meters is longer than a large SUV. It's like a small bus. Just try to picture a lizard that big.
And what's even crazier is that we've had to build that picture from fragments. We've never found a complete single skeleton of one.
Right, that's a key point. So these aren't just wild guesses. How do paleontologists get from, say, a single vertebra to a 7-meter monster?
Well, it's a game of ratios, really. You look at its living relatives, the varanids or monitor lizards. You measure the bones of a Komodo dragon. You see the ratio of its spine to its total length. And then you apply that same ratio to the fossilized bones of Megalania.
So you scale it up.
You scale it up. And that's why you'll see a range of estimates in the research, from 4 to maybe 7 meters. That 7-meter figure, that's the max size calculated from the biggest fragments ever discovered.
And we know where it came from. This whole lineage of monitor lizards, they started out in Asia, 100 million years ago?
Something like that, yeah, late Cretaceous. And they migrated, eventually spreading all across Australia and evolving into this absolute behemoth.
And it wasn't a slow, lumbering beast either. I saw a speed estimate of around 10 kilometers an hour.
Which might not sound that fast, 3 meters a second. But you have to imagine a 2-ton, 7-meter carnivore closing that distance. It was more than fast enough to ambush just about anything it wanted to eat.
And we've known about it for a while. The first fossils were found back in the 1850s.
1858, yeah, by Sir Richard Owen, the man who actually coined the word dinosaur. He found them near the Condamine River in eastern Australia and knew right away he was looking at some kind of gigantic, ancient reptile.
Which brings us to the next big question. How do you power an engine that massive? What was it eating, and how is it killing it?
Well, its diet had to be broad. We're talking about the giant marsupials of the time, other reptiles, big birds, basically anything it could sink its teeth into.
And those teeth were pretty serious weapons.
Oh, yeah. They were large, they were curved, and they were serrated. Think less like the stabbing teeth of a big cat and more like the edge of a steak knife or a shark's tooth. They were built for tearing off huge chunks of flesh.
Okay, but here's where I get a little stuck. The sources say that monitor lizards, even the Komodo, have, relatively weak skulls and bite forces compared to something like a crocodile.
That's absolutely right.
So if Megalania was hunting these huge animals, why wasn't it just a giant scavenger, picking off things that were already dead?
That is the critical question. And it's the exact reason the venom debate is so important. That apparent weakness, the weak skull, the low bite force, that's precisely why the venom hypothesis is so compelling. It's the biological workaround.
The great equalizer.
Precisely. The theory, and it's a strong one, is that Megalania, just like its modern cousins, could deliver a venomous bite.
And if that's proven true, it would make it the largest venomous animal to have ever lived. That's a huge claim. What's the actual evidence for it?
Well, we don't have fossilized venom glands, of course, but the circumstantial evidence is very strong. First, we know many living monitor lizards have venom glands in their lower jaws.
Okay.
Second, when you look at Megalania's fossilized teeth under a microscope, you can see these distinct grooves running down them. In modern venomous reptiles, those grooves help channel the venom from the gland right into the wound.
And this wasn't like a cobra's neurotoxin, it was a different kind of venom.
A completely different cocktail. It was full of anticoagulants, which stop blood from clotting, and other compounds that cause a catastrophic drop in blood pressure. Hypotension.
So the prey goes into shock.
Exactly. Megalania wouldn't need to win a wrestling match. It could just run in, deliver one quick, shallow bite to a giant kangaroo or a diprotodon, and then back off.
And just wait.
And just wait. The venom does the work. The animal bleeds out. It goes into shock. It collapses. Then Megalania just strolls over to claim its meal. No risk of getting injured in a prolonged fight. It's an incredibly efficient, chemically driven ambush.
It's terrifying.
Right.
And you have to remember the world it was living in. Pleistocene Australia was it was a land of giants.
An unbelievable landscape. I mean, it helps you understand the kind of competitive pressure that created a predator like Megalania. It was sharing the land with creatures straight out of a fantasy novel.
Like the diprotodon, basically a wombat the size of a rhinoceros. A huge, slow-moving herbivore.
Talk about a tempting meal. But then you also had other massive predators like Thylacoleo, the marsupial lion, a bone-crushing ambush predator.
And there was a sheep-sized echidna and that giant kangaroo, Procoptodon, that stood 10 feet tall.
And in that field of giants, Megalania was the undisputed king, the apex of the apex predators.
So it had this other amazing advantage, this biological superpower that helped it deal with the Pleistocene's crazy climate swings.
Right, because that whole era was defined by these dramatic shifts. It would go from cold, dry, glacial periods to warmer, wetter times and back again. Really unstable.
And Megalania's physiology was perfectly suited for that.
It comes right back to it being a lizard. Monitor lizards are masters of surviving when resources are scarce. They can gorge themselves on massive meal. We're talking up to 80% of their own body weight in one go.
80%.
And then they can digest it incredibly slowly. They can basically function on one huge feast a month.
Which is a huge advantage. So when a drought hit or the environment crashed, Megalania could just wait it out. It could outlast all the mammalian predators that needed to eat every few days.
They should have been almost indestructible. Which, of course, brings us to the biggest mystery of all. If this creature was so perfectly adapted, so hard to kill, why did it disappear?
Right. It survived all these massive climate shifts. But then, around 50,000 years ago, it vanishes, along with most of the other megafauna.
For a long time, climate change was the go-to answer, but that theory is now really, really contested.
The evidence just doesn't fully support it, does it?
Not really. The fossil record shows that megafauna populations would shrink and shift their territory during tough climate periods, but they didn't just collapse entirely. They always bounced back. If climate was the only killer, we'd expect to see a much more gradual decline over many cycles. We don't see that.
So if it wasn't the climate,
Yeah.
what was it? The timing points to one thing.
One new, game-changing variable, the arrival of humans in Australia.
The timing is almost a perfect match, isn't it? Humans show up around 50,000 years ago, and soon after, the megafauna starts a steep terminal decline.
The correlation is just too strong to ignore. The debate now isn't so much if humans were the cause, but how. What was the actual mechanism of impact?
And there are a few leading theories on that. It's probably not just one single thing.
No, almost certainly a combination of pressures. The first and most obvious is overhunting. Now, hunting a full-grown 2-ton Megalania would be incredibly dangerous.
A suicide mission, probably.
Pretty much. But early humans were smart. They could have systematically targeted the young, the juveniles, and if you consistently remove the next generation from a population, it doesn't take long for that population to collapse.
Then there's the idea of disease. Humans brought new pathogens with them that the native wildlife would have had zero immunity to.
Exactly. A new disease could have swept through megafauna populations like wildfire. But the theory that's gaining a lot of traction right now is habitat destruction, specifically through fire.
Humans using fire to manage the landscape.
Right. So-called fire stick farming. They would burn huge areas to clear paths, to encourage certain plants to grow, or to flesh out game. This constant, widespread burning would have completely transformed the ecosystem that the megafauna depended on.
So it's the cumulative effect. Megalania could survive a 1,000-year drought by just slowing its metabolism down. but it couldn't survive having its entire food web systematically dismantled from the bottom up.
It was an entirely novel pressure. It was adapted for nature's cycles, but it was completely unprepared for an intelligent species that could fundamentally reshape the environment itself.
And it's so important to remember that for all we've discussed, our picture of this animal is still so incomplete.
That's the challenge, but it's also the excitement of paleontology. Like we said, no complete skull, no fully articulated skeleton. Our understanding is built from pieces, a puzzle we're still trying to solve.
Every new fossil discovery adds another piece to that puzzle.
It does. With every new fragment we find, this massive lizard king becomes just a little less lost to time.
Okay, so let's try to bring this all together for you. We've got this 7-meter, 2-ton lizard, a predator so massive it likely used a toxic, venomous bite to take down giants.
An animal that possessed a biological superpower, the ability to fast, that let it survive devastating climate swings that other animals couldn't.
And yet, that supremely adapted creature was ultimately undone by the arrival of one new species on the continent.
It really highlights how complex extinction is. Megalania's unique survival strategy was perfect for weathering global climate change. But that same strategy was useless against the rapid, total environmental impact of early humans. It just tells you something about the sheer speed and power of our species' impact, even 50,000 years ago.
Which leaves us with a final thought for you to chew on. The sources mention that many of the earliest human settlements were on coastlines that are now underwater, lost when the ice caps melted. So if human arrival on land triggered this massive extinction event, what other giants, what unknown marine megafauna might have been lost to the seas right alongside those early settlements before we ever even knew they existed? Something to think about until our next deep dive.